All right, we are getting to our countdown of the end of statistics. We've really just got two main concepts left, and they're both tests, hypothesis tests that we have already kind of done before. So it's going to follow the same kind of logic and the same kind of thinking that we've already done. So let's take a look. We are going to get a little cup of M&Ms today, and we're going to then count all of the colors in our M&Ms, not just the blue M&Ms like we have done in the past. So we're interested in all of the colors that are claimed to be in those M&Ms. The Mars Candy Company claims that each color's true proportion of M&Ms that are made and distributed are as stated: 13% brown, 14% yellow, 13% red, 24% blue, 20% orange, 16% green. All right, so I got a little cup of M&Ms, and I counted that. And what I got in my cup of M&Ms was this. It had a total of 62, which, by the way, my cup is a little more than the actual M&Ms bags, because those typically have about 54 to 56 M&Ms in them. So I got a little bit more. But anyway, here was the count distribution that happened. Okay, now here were the percentages that are expected to happen, but here are the actual counts. Okay, so let's tie this to something we already know. If we were only talking about blue M&Ms, then what hypothesis test would we use to see if there's a statistically significant difference in a claimed proportion of blue M&Ms? Well, I kind of actually answered a little more than I was supposed to right there. The hypothesis test that we would be doing then is going to be that one proportion Z test. Okay, for one proportion of blue M&Ms. And we would start it off saying that P equals the proportion of blue M&Ms. Our null hypothesis would be that P is 0.24 because that was the claimed 24. And then alternatively, we're just seeing if there's a difference. So that's why I did a not equal to. Okay. So let's go do that for the blue M&Ms. I got 13 of them. So let's see what would happen. Assuming all the conditions for inference are made, yay, we're going to run a significance test for what we stated above for the blue. So population stated to be 24. I had 62 M&Ms, and see, you are going to do this for your own particular cup of M&Ms because I want to see how did your values compare to what they were expected to. My sample was 13 out of 62, so 0.21. It was expected to be centered around 0.24, and then here was that standard deviation. So my z-score was my sample results minus where they're supposed to be centered. And so that's a z-score of just negative 0.56, not unusual at all. So one tail's p-value was that I went ahead and went more extreme, which since it's a negative z, more extreme would be the lower. So 29%, not rare at all. But now remember, that's the p-value for one tail. Since we were just seeing if there's a difference, my HA was two-tailed. So technically, remember, for two tails, I'm going to total two tails worth of p-value together. So 0.5824. 58.24% chance that I would have gotten that sample results I got, or something more extreme, if the true proportion of blue M&Ms is 24%. Not unusual whatsoever. So here we go. So my p-value is definitely greater than alpha. I fail to reject. I don't have any evidence that the proportion of blue M&Ms is different than the claimed 24%. Okay, but now we're going to see what happens if we want to do a collective testing out for all of the hypothesized colors at a time. So we're coming to this concept of not one proportion, not even two proportions, but multiple proportions. That's what we have here. This is called a chi-squared test. And there's a few different kinds, and so we'll talk about what those are and why there's different kinds. But one proportion z-test, two proportion z-test, and now we have this multiple proportions, and that's called chi-squared. So here's how we would do this. We would first run a test, and we would start off saying, hey, the null hypothesis says that the M&M colors are distributed as stated. Now, you are welcome to write out all of those percentages, but we don't have to. We can just say distributed as stated in the prompt or as told to me, whatever. Now, alternatively, what do you think that's going to be? That the M&M colors are not distributed as stated. Maybe I suspect, whoa, I got some really weird numbers here. I don't think they're really putting out what they claim. Well, let's see what we got. Okay. So you're gonna fill in this, and I've done this here, and so let me actually kind of section this off so that we can kind of take it a piece at a time. So, of course, you see over there on the left my observed values. So look, I even wrote those as observed. Okay, so here we go. Let's do this here. All right, so over here, the observed values, what actually happened were these numbers right here. And then I think there was a green one down there. Okay, now what's going to happen next is we want to investigate what was expected to happen. And these have to be in counts, not percentages. So it may be tempting because we've done this when we did our z-tests. We would do this in terms of proportions, okay? So, but we actually do these in terms of actual counts, not the percentages. So I observed for brown, but I expected to get 8.06 brown. How did I come up with that? Well, for my sample, N is how many? I had a total of 62 M&Ms, and 13% of them were supposed to be brown. So 62 times 0.13 is your 8.06. So that is what was expected. All right, and then for the yellow, 62 M&Ms was what I had, times what was supposed to happen, 14% yellow. So that was 8.68, and so on. So I have those listed out for each one of my colors. Okay, so here we have it. I see what was observed, what actually happened. I see what was expected to happen. So I can see I've got a little discrepancy. Let's kind of look at those. Brown was a bit off. 13. Blue wasn't too bad. It was 13 and expected was 14.88. So see, so very close. Look at orange, 17, and what was expected was 12.4. It looks like maybe, is that going to be my biggest discrepancy? That one. Yeah, and that's a little bit more than the brown. But looks like that was, so the biggest discrepancy I had were the oranges. And I don't know how unusual that was. I would have to run a hypothesis test for just orange if I wanted to just do that. But let's keep going. So next we're going to get a component. And this is going to be essentially each individual category or separate component, each component categories that we're talking about here, every single one of their discrepancies. So I'm going to see how far is what I actually got observed away from what I was supposed to get. Okay. And then do you remember that idea when we did standard deviations, how we couldn't add add the positive discrepancies with the negative discrepancies? Because if we added those discrepancies together, that equaled 0, and that was not informative to us in terms of like standard deviation. What kind of discrepancy? How far is this off? So remember, we squared those to account for that. That's what's happening again here. So we've got the observed minus expected, square it, and we don't have this standard deviation or whatever, so we're doing it in terms of expected. Okay, so that's what they want to do relative to what was supposed to happen. How far off are we? That's kind of what's happening. Let me say that again. Relative to what was expected to happen, how far off was our observed data? Okay. So here's how that would look for one of my colors here. So my observed brown. So I got 4 minus 8.06, quantity square that, and then divide by the 8.06. So that's 2.0451. I went ahead and did quite a few decimals, only because I knew my calculator was going to give me quite a few, and I'm going to be doing this shortly in my calculator. Okay, so then I'm going to invite you to do that with all of your data. So let's see what the component, oh, look at there. Look at that, 0.2. So that was, yellow was relatively close to expected. Okay, in terms of its expected. Okay, let's see, red, not too far off, 1.07. Okay, there was the blue. See how close that one was? Yeah, almost as close as yellow. Let's look at that orange one because I thought that was the biggest discrepancy. Let's see what's happening here. 1.065. So that's interesting, right? Look at that. Why is that brown? Look at that. Brown actually has a bigger component than orange. Why is that? Well, that would have to do with what you're dividing it by. Here you were dividing it by a smaller number. So in terms of what was expected, you're actually a bit farther off for brown than orange. Okay, so you kind of see how that works. And then we got one more left, the green. So let's see, 0.8595. Okay, so the final thing to get a full total test statistic, a whole idea of the collective discrepancy of all of our categories, is the summing of those components. So when we sum those components up, we get what is called this chi-squared value. Chi-squared, not chi, C-H-I. It is spelled C-H-I, like your hair products, but it's not chi, it's chi, like chi omega, the Greek letter chi. So, and it's not like chai tea either. It's not chai tea and it's not chi for your hair products. It's chi. All right. So chi-squared is the sum of all of those discrepancies, and I was 6.12 off. So think of it like I'm that many standard deviations away from what was expected to happen. Okay. But the thing is, chi-squareds are much more much bigger because it's a collection of many discrepancies. So getting a chi-squared of 6.12 really probably isn't that big of a deal. In fact, I would venture to say that tomorrow when I do this in class, that's one of the smaller ones, or at least pretty centrally located as far as the discrepancies. So we'll see, and I'll show you our collective class results tomorrow for all of our everybody's chi-squareds. Okay, so let's look at this on the formula chart. So this is on the formula chart, and I'll show this to you at a later point, but it's the chi-squared statistic. It's like a Z, it's like a T, it's a measure of that discrepancy from what you expect. Chi-squared is the summation of all of those components. Observed minus expected, quantity squared over expected. Done. That's the main idea of what's happening with chi-squared. a collection of the discrepancies of multiple proportions, multiple categories. Okay, here was just another example that I had. Oh, look, that one I got 3.14, so that was even closer. Okay, so let's go on to the next page. And what is going to happen is here you're going to kind of answer some questions. You may consider pausing this and think about these. These are really investigatory questions. So, for advanced students, these are the type of things that you should kind of be able to think out of the box about. Um, so, if you want to pause, ponder these, and then come back and start again, then we'll go over the answers. But here we go. Pause if you want to ponder these on your own. All right, so here we go. We're going to investigate some questions. So, what do you think chi-squared value is representing? I've kind of said this several times. I think it's that collective discrepancy that the actual values are away from what's expected collectively for all those categories. Okay, now this is interesting. What is the domain of the chi-squared values? Domain. Okay, so that's like x. So think in the x direction, domain. What do we got? Well, they're chi-squareds. Since the observed minus expected is squared, then what do you have to say about that chi-squared test statistic? It's got to be positive. Therefore, the domain is all real numbers greater than or equal to 0. So very interesting. All right. What do you think that means if we have a really big chi-squared value? The bigger your chi-squared value is, what is that saying? Well, then you have a bigger collective discrepancy that the actual is away from what was expected. So the bigger the chi-squared, the farther away your actual was from what was expected to happen. Well, what about the smallest? The smaller the chi-squared, what does that mean? That would mean that you are getting really close. Your actual observances, what actually happened, what was close, very close to what was expected to happen. So, very small discrepancy. Okay, next. Ooh, what would the smallest chi-squared value mean in context of our M&Ms? I wonder if I I didn't answer this correctly because I wasn't thinking about what would the smallest chi-squared value mean? Well, it would mean that you got your M&Ms were exactly what they were expected to be. So I need to probably rewrite that answer. But 0 is the smallest that it could possibly be in real world. I mean, in technical terms, because that would mean every observance was exactly what it was supposed to be. Okay. Is that chi-squared value, a value of 0, actually possible for our M&M problem? Why or why not? Well, for me it wasn't. I had 62 M&Ms and you remember that my expected values were decimals. My expected values were decimals. So there was no way I was going to be able to get the exact expected amount. I'm going to throw back a past vocabulary to you because we can't get that fraction of an M&M in real world terms. So what's happening is this. Those expected values are continuous because they were decimal points and they could be infinitely many small. But my observed data is discrete. That was a whole number amounts of types, colors of M&Ms. So I mean, maybe if I had 100 M&Ms and then those percentages all came out to be whole number amounts, Then I could have gotten a chi-squared value of 0 if my observed was exactly. But if I didn't have those whole number expected values, then I wasn't going to be able to get 0. All right, what about this? Do you think that the shape of the data for chi-squared curve is going to look like the normal model? Why or why not? Okay, so I want you to think of the domain in this case. What did we say the domain was earlier in this? We said the domain was all positive numbers, 0 and up. But what's the domain for the normal model? The normal model is centered at 0, and it goes from negative infinity to positive infinity, whereas this chi-squared curve is going from 0 to positive infinity only. So, do you think this chi-squared curve looks like the normal model? And that answer is definitely no. I can tell that for sure. Now, at this point, I may not know what it's going to look like, but it won't be like the normal model because I can have negative test statistics with the normal model, and I cannot have negative test statistics with the chi-squared. Okay, how about this one? Do you think that the number of categories in the problem has an impact on the chi-squared test statistic that is considered significant? Why or why not? Did I talk about the shape of, okay. Okay, number of categories. Okay, so for example, in our problem, we had 6 different colors of M&Ms. So, but you could have other problems. If you were doing Skittles, how many colors do they have? 5. I saw somebody doing some of these things with, say, they were doing bottle caps. They had their students take some of their Easter candy and do some chi-squared tests with that. And somebody did them with bottle caps, and I think there was just 4 colors for bottle caps. Okay, so what's happening with the number of categories? Because I'm thinking to myself, if I have more categories, then I have more discrepancies that I can sum up. So if I have more discrepancies I can sum up, then I think my chi-squareds can be bigger. Okay. So for the bottle cap people who only had 4 colors to try and match up, they're going to have smaller chi-squareds probably than us who has 6 discrepancies to deal with. 6 different colors. Okay. So yeah, I think that those numbers of categories is going to have an issue. I mean, going to deal with what's considered significant. What's way far out for the bottle caps may not be way far out for our M&Ms. Okay, something to think about. Okay, how about this? Do you think that the number of categories contributes to the chi-squared test statistic? Or does that have an impact on the shape of the data, the shape of the distribution? Why or why not? And, at first that just seems like weird to think about. But when I think about this question right here, yeah, I think so. I think the shape of a whole bunch of people doing bottle caps problems with only 4 colors, categories, I think their data is going to kind of be squinched closer together. It's not going to be they're not going to have quite as big of chi-squared numbers as those of us who have 6 colors to deal with. If we have 6 colors to deal with, I think we naturally are going to have bigger chi-squared values. So I think our data will be more stretched out than somebody that just has a couple of categories. What do you think about that? So I think I wrote that out here. Let's see. I think the number of categories would impact the shape. When you have just a few categories, I think the chi-squared values are generally smaller. This makes me think that more data is kind of squished up, going to be closer to 0 because the chi-squareds are smaller. But what if I have more categories? Then I think it's much easier to get bigger chi-squared values. And so if it's easier to have bigger chi-squared values, then they're more likely, more probable. So hence I think the more data is stretched out and farther away from 0. So yeah, I think that the number of categories is having an impact on the shape of this distribution and what's considered unusually big, so that it makes me go, whoa, that's an unusual discrepancy that I have, collective discrepancy that I have. So that takes us to the next video. I'm going to stop this one right here. The next video is going to reveal to you the shape of the chi-squared distribution. All right, so I'll see you in the next one, and we'll put an actual picture and shape to this thing we've been pondering about, our chi-squared distribution.